So in our prior video, we showed you how to fold a sheet of paper into thirds or fifths, and in this video, we're going to show you why that happens mathematically. So what I did was I highlighted each crease I made last time with a red line and a blue line. And we're going to actually take these creases that we made last time, and we're going to express them as linear equations, the y equals mx plus b equations you've been learning in class. So if we're going to do that, we're going to need a coordinate system. So I bring my handy dandy coordinate system in, and I put my sheet of paper on there, and I run into a problem. There's no sort of way that I can quantify how big this sheet of paper is. So I'm going to also say, let's assign it a height of 1. Since it's a square, the width is also 1, which means that I can generate these points. We have our origin, and since it's a square, we also have the furthest point being 1, 1, and respectively 0, 1, and 1, 0. Now what we're going to do is we're going to take the red line, define it as an equation, take the blue line, define it as an equation, and then solve for the intersection. So the first step is finding what these equations are. So starting off with the red line, we know that our slope is equal to rise over run, which mathematically is y2 minus y1 over x2 minus x1. Our y2 point here is 1, and our y1 point is 0. Our x2 point here is 1, and our x1 point here is 0. So our slope is equal to 1. And we see that the intercept here is just 0. So our equation y equals mx plus b is really just y equals x. And that defines the red line. Now we need to define the blue line. So we grab a new sheet of paper and a new color-coded marker and set off to work. So blue line, we have our slope. As always, we start off rise over run. Mathematically, y2 minus y1 over x2 minus x1. Our y2 point here is 0. And our y1 point here is 1. Our x2 point here is a half, and our x1 point here is 0. So we get negative 1 over a half, which is equal to negative 2. And we see from our sheet of paper that our intercept is 1. So b equals 1. And our equation, y equals mx plus b, is therefore just negative 2x plus 1. That's all it is. And now what we're going to do is set the two equations equal to each other. We're going to have the blue line equal to the red line. And I'm going to work in black so that way I don't have to switch between the colors every 2 seconds. So our blue line we found was negative 2x plus 1. And our red line we found was just x. So what we're going to do is add 2x to each side because we want to get rid of this negative 2x. But what we do to the left side, we have to do to the right side. So we add 2x to each side. These two 2x's will cancel, and these two will add. So we end up with 1 equals 3x. And then we just divide each side by 3. And we get 1/3 equals x. Pretty simple. And we can now prove mathematically that when I did fold it, it was exactly a third. You weren't just taking the word of some random guy in a video. And I encourage you to go try this with a quarter and see that that also equals a fifth. And if you are curious about generalizing this, find out how to make any subdivision you want of the sheet of paper. Try using a variable instead and see if you can't come up with a formula to divide a sheet of paper into any amount of fractions you want. It's pretty fun. Try it out, and I hope you enjoyed this. If you want to learn how this folding a third relates back to the stellated dodecahedron in the first video, check out the next video and you'll see how it does. You'll notice that we get one of the spikes that we require. And then this will be used for another spike, and this will be used for another spike, and this will be used for another spike. And when you use all the spikes together, you will end up with a stellated icosahedron.